Hi everyone! Today in this lesson we are going to talk about the minimum spanning trees and its applications. So let's start with some example. Assume we have 6 machines in our office. So here is 1, 2, 3, 4, 5, 6 machines and we have to join them. So we put wires between some pairs of them such that any machine is reachable from other machine. Assume further that we can put wires only between some pairs of them. And here we have a cost on every wire. So for example, we can put a wire between this and this machine, but for example, we cannot connect this one with this one by wire. So now we have to find a way to join each network with each other with a minimum cost. So one of the optimal solutions is shown here. So here we can see that every machine is reachable from other. So for example, if we take this one and we would like to connect with this one, we will be having a path like that from this to this, then to this one, then finally we can reach this machine. And this works for all the machines. And the wires that we have put, the total cost of them will be the minimum possible, the one of the minimum possible cost that we can put here. So for example, instead of this one we can put this wire, and it will also be right because the cost of this one is 2 and this one is also 2, and there will be like no difference if we would be choosing this one. And the total cost of this one will be 2, 3, 3, $12 will be the total cost for such a problem. So formally, the minimum spanning tree, to construct a minimum spanning tree, we will have in the input a connected undirected graph with positive edge weights, and the tree will be a subset of edges, we will call it E prime, of minimum total weight such that the graph is connected. So if we leave this subset of edges and we'll remove the other edges, the graph will still connected. So why does this problem called minimum spanning tree? And the minimum stands that we want to find a tree that have the total minimum weight of an edges and spanning that because the graph is still connected, so it spans all the vertices in our graph. And the tree, because in the output the set of E prime is going to form a tree. And we will now prove it in the next slide. Before proving it, let's remind the properties of a tree. A tree is undirected and acyclic. Here will be an example of a tree. So we see that there is no direction of an edges, and it has no cycles and it cannot have any cycles. And then the next property of a tree is that a tree on n vertices has exactly n minus 1 edges. So here, for example, we have 1, 2, 3, 4, 5 vertices and 1, 2, 3, 4 edges. 4 edges. And then also next property is that any undirected graph, GVE, such that the vertices will be one less, the edges will be one less than the vertices, is a tree. And the other property states that an undirected graph is a tree if and only if there is a unique path between any pair of its vertices. And this is also easy to prove because, for example, we have here in a tree we have one unique path between two vertices, and if we will have another path here, so the it will not be unique, and we will have a cycle which is not this giving us a cycle, and it cannot be a tree anymore.
Hello, so today our topic is greedy algorithm. So first of all, let me introduce you what is the greedy algorithm. So greedy algorithm is an algorithm paradigm that follows the problem-solving approach to making the local optimal choice at each stage with the hope of finding the local optimum. So greedy algorithm is simple, easy to implement, and runs fast. So let me give you some examples of when to use the greedy algorithm. So when we can use the greedy algorithm. So first of all, the greedy algorithm have the greedy approach as the two properties. So first one is the greedy choice property. It means that the global optimum can be arrived at by selecting a local optimum. So the second one is the optimal substructure. An optimal solution to the problem contains an optimal solution to the subproblems. So the example. So this is the example. We take some tree with some numbers and then apply the greedy approach. So first one, we take the 7. Then we take the optimum one here. So it will be the 12. And the next optimum one between them is 6. So when we apply the greedy approach, our sum will be 25. But when we apply the optimal structure, it will take first of all 7, then 3, then 9. So our answer will be 109. So the application of the greedy algorithm is the activity selection problem, Huffman coding, job sequencing problem, fractional knapsack problem, and Prim's minimum spanning tree. So next one I will explain you the example for the minimum spanning tree. So there is the two greedy algorithms where we can use this minimum spanning tree. The first one is the Kruskal algorithms. The Kruskal algorithms that repeatedly add the next lightest edge if this doesn't produce a cycle. So the second one is the Prim's algorithm. So repeatedly attach a new vertex to the current tree by lightest edge. So I will draw you the examples here right now. So as I said before, here's our Kruskal algorithm example. So there should not be a cycle. So the first one will take the smallest weight. So this one will be 1. So we can add it. So the next one is also 1. So as you can see, we can also add it. So the next one is 2. We can apply it, but if we can take 3, it will be the cycle. So our Kruskal algorithm does not produce the cycle, so we cannot apply it. So next one will be 4. We can apply the 4 because that will produce the cycle. So by this way, you can produce the Kruskal algorithm. So our second example is the Prim's algorithm. So as I said before, it repeatedly attaches new
mostly considerable to algorithms construct the solution iteratively. Namely, they start with an empty solution with an empty set of edges, and at each iteration, they expand the set of edges by one edge. And the question is how to select another edge to be connected between two cuts. So let's see the example first. In this example, we assume that we started to find the minimum spanning trees, and they are denoted by orange lines, orange edges. And what is a cut property? It states that the vertices that are connected with each other are they're like creating a new cut. For example, here all the vertices are connected by each other, and so it forms a cut. Also here the vertices are connected, and they are forming another cut, and the vertices from this one and this cut is not connected, so they are in different cuts. And now we have to find a way to join them, but not just find a way, find the least weighted edges to connect them. And cut property states that the edge that connects these two cuts will be definitely in the final spanning tree that we will found. So if this edge will be, for example, the minimum cost edge from these three ones, from these four ones that are connecting two cuts, this means that this edge will be in the final spanning tree. And to find this edge, we have actually two different strategies. The first one, the Kruskal algorithm, it selects the next lightest edge that doesn't produce a cycle, while Prim's algorithm selects the next lightest edge that attaches a new vertex to the current tree. We will talk about it later, and we will show the examples. And here what we need to prove is to show that both algorithms is optimal solution, that these strategies are in some sense safe. At the current step, we have a subset of which we called E prime, which is a subset of some optimal solution. And then, as I said before, by adding this edge, assume we had this edge in our MST. So here we can clearly see that here will be a cycle. So for example, and here this one will be also selected. And here we can see that these vertices are creating some kind of cycle. So here we can see that the one of these edges are an extra edge in our spanning tree. And if this one is cost less, we will choose this one, then this one, and this one we will remove from our resulting spanning tree, and all the properties will be will not change, and the subset of edges, and this graph will still connected, and there will be no cycle. So this is a property of a tree.
So our next step is Kruskal's algorithm. So algorithm is repeatedly add the x, the next lightest edge e that doesn't produce a cycle. So at any point of time, the set x is a forest that is a collection of trees. So the next edge e connects to two different trees. Let's say T1 as here and T2. So the edge e is the lightest between T1 and b minus T1, hence adding e in the set. So let's take here this graph at T1, and this one is at T2. So here we apply the edge that will not make a cycle, so we call it e. That's it. So here's the implementation details. So the first one is the use disjoint sets data structures. The second one is that initially each vertex lies in separate sets. The third one is that each set is the set of vertices of a connected component. The last one, to check whether the current edge UV produces a cycle, we check whether UV belongs to the same set. So here, for example, if we apply here the E edge, it will produce the cycle, so we cannot apply the E here. So for example, if we apply here E, it will not produce the cycle, so we can apply the edge E here. So here is our example. Here we will construct the optimal spanning tree. So let me show you. First of all, we will look at the weights of the graph. So as we can see here is that A to B is connected. So B and E is connected, and the C and F are connected here. So first of all, we look at the smallest weight here. So first of all, one is here, so it's connected. So we can write here the AE. So we can raise the E. The next one. Which one is the smallest one? Here's one from C to F. Here's the so we are right here C to F. And the next one. Which one is the smallest one? Here's the 2. So also we'll write here the D. And the next one, we can take the 3 here, but it will produce the cycle, so we will not take the 3 here. So the next one, B, from A to B, it will not produce the cycle here, so there is a cycle, so we will B here, B. So the last one, we just add the CF to this part, so by this way, we construct the optimal spanning tree here. So here is our sample code here. So first of all, for each vertex in our graph, we create separate disjoint set here. So we call the method make set here and initialize the x as an empty set. So as written here, you can see that we sort the HC by its weight, and for all U and B, and in not decreasing order. So here, starting from here, we should check whether it produces cycle or not. So here we compare the find U and find B here. So then, if it's not cycle, then that vertices to U and V to our set, and in the end, then return our set. So this is the total running time.
The Prim's algorithm. By definition, let's say that x is a subtree, and it grows by one iteration at a time. Then we add a lightest edge between the vertex of the tree and the vertex not in the tree. And also this algorithm is very similar to the Dijkstra algorithm. So let's take a look at an example to better understand. in this example, we have some undirected graph, and for example, let's consider we will start from this vertex and we look which edges is lies to this vertex, and this is in our case it's 1 and 8, and if we start from this one, we will choose the 1, of course, because it's less than 8. Okay, now we're now here, and we have two choices, 6 or 9. We will go to there by 6 because it's less. Then we have 5 and 5, 4 and 8. We will go to the 4. And then we have a choice like 1 and 2. We go by 1, and the last one, now we have a single vertex that left. These are the visited vertices. We will make it like this, and the one that left is this vertex, and here we just must look which one is less, 3 or 2, and here we will pick the 2, and here is the total minimum spanning tree, and now we will have a look at the code. So here we have a class prims MST, and so we start from creating the minimum priority queue, and our final minimum spanning tree will be in the structure of queue. And also we will have to monitor the visited vertices, so we will have an array of booleans called marked. And here we start by creating the minimum priority queue, initializing MST priority queue and this array. Then at this line we will visit all the vertices that are adjacent to this one, and then here we started from 0, but we can actually start with some random vertex which is in the graph, and then while our priority and here in that method we will insert the vertices that are adjacent to this one into our priority queue, and then while priority queue is not empty, we will extract the edges from priority queue. We will take the minimum one and then check if the vertices are visited, then we should just continue, because if they are both visited, that means that they are already in our minimum spanning tree. Otherwise, we will insert this edge into our minimum spanning tree, and then look through all other vertices. So of course, if they are not marked, so we should visit that particular vertex, and here should be W. So by that we will achieve a minimum spanning tree by the prims algorithm.